Welcome everyone. I'm Janita Vanasundara, research scientist with Agriculture and Agri-Food Canada, Saskatoon Research and Development Centre. My research program is on plant protein chemistry and utilization. So today's webinar topic is, and the content is very dear and near to my research area, and glad I have the opportunity to moderate the webinar. It's my pleasure to introduce the two great presenters today. Dr. Michael Nickerson, Saskatchewan Research Chair for Protein Quality and Utilization, University of Saskatchewan, Canada. Dr. Nickerson received his Bachelor of Science, Masters, and PhD from Dalhousie University in Halifax, Nova Scotia, Canada. Currently, he is the Saskatchewan Ministry of Agriculture Research Chair and professor in the area of food quality and utilization within the Department of Food and Bioproduct Sciences at the University of Saskatchewan. His research area focuses on improving uses of plant protein ingredients within food industry, with the emphasis on fractionation, ingredient modification, and protein functionality. His program has led to 160 plus internationally peer-reviewed publications and receives funding from provincial, federal, and industry sources. Dr. Nickerson's program focuses heavily on graduate student training to meet employment gaps within protein ingredient sector. Dr. Tulbek is the director of AGT Foods Research and Development Center in Saskatoon, Canada. He is our second presenter who will follow up from Dr. Nickerson. He has over 20 years experience in cereal, pulse, and oilseed processing and utilization technologies. Dr. Tulbek completed his BSc in agriculture engineering with the emphasis on food science and technology at Ankara University, Turkey, and Master of Science Food Engineering at Istanbul Technical University in Turkey. He has a PhD in cereal science from North Dakota State University, Fargo, North Dakota, USA. Before joining AGT Foods, Dr. Tulbek worked at Northern Crops Institute as crop quality specialist and as the technical director. Mehmet is a sought-after presenter at global industry and academic gathering, and he has presented webinars in AOCS as well previously. He has authored numerous journal articles, book chapters, and proceedings. He's a member of multiple organizations, including IFT, AOCS, CIFST, CNS, Canadian Nutrition, I believe, AAFCO, and Cereals and Grain Association. Currently, he serves as an adjunct professor at the University of Saskatchewan Department of Food and Bioproduct Sciences and University of Manitoba Department of Food and Human Nutritional Sciences. Please write any questions for our presenters into the question section of your control panel. All the questions will be asked and at the conclusion of the webinar. And so good morning, good afternoon, and good evening, depending on the geography you are joining from. And thanks again for joining. And now I will return it over to Dr. Nickerson to start the webinar.
Thank you, Janita. Welcome, everybody. We're really happy to do this webinar for you. I just want to give a quick outline of what we're going to talk about today. We're going to give you a little introduction about plant-based foods, go into some ingredient and enhancement technologies, look at some functional properties of plant-based ingredients, and we'll focus more on the protein ingredients for this talk. And then move into some formulated food systems and low and high moisture foods of how we can start incorporating these ingredients into different products. So just to give you a quick overview of the plant-based food market, by 2027, it's expected to reach about 74 billion globally with a compounded annual growth rate of 11.9%. And as you know, when we talk about plant-based foods, it refers to a variety of food products derived from a number of different plant sources. We can see some examples here in the pictures of tempeh, meat analogs, non-dairy milks are just some examples, and we'll hear a little bit more later when Mehmet gives his talk about some other products that we can use these plant-based ingredients for. So what's driving, what are the macro drivers driving the plant food trend in the industry? Well, there's a number of macro drivers. One is global population. How are we expected to feed 9 and 10 billion by 2050 in a sustainable manner? So finding attractive and cheap sources of high quality protein, for instance, to feed that world population is really important, and plants have a big role into that. There's also another macro driver, environmental sustainability and ethics associated with livestock agriculture. Livestock is much more land intensive than the plant-based, so there's a sustainability issue being driven in the marketplace. Urbanization as well, so we see a lot of rural populations moving to urban centers, and with that we see a change in dietary patterns to a more diverse diet, including the plant-based foods, which are driving demand. Some other macro drivers in the plant food-based sector is changing demographics. Right now, globally, 27% of population is millennials, but in China and India and Southeast Asia, it's closer to 57%. And these millennials tend to stay at home longer. They have more buying power, and they're more apt to trying new, different alternative sources of foods in their dietary patterns. So they're more apt to go vegan or try plant-based foods in the marketplace. There's also some health concerns associated with the consumption of animal products associated with cardiovascular disease, which is driving some movement in the plant-based sector. And nutritional regulators. So a good example is in Canada, we just came out with a new Canada's food guide, which reduces the amount of dairy protein in response in favor of more plant-based sources such as nuts or pulses or other legumes. So there's some regulatory influencers that are driving this. Now, there are a number of plant-based sources, and we don't have to go through all of these, but some of the really interesting ones from a proteins perspective is rice, oats. Pea is obviously a really big one, hot topic in the food industry, but also some of the other pulses like fava bean is really of big interest. Oil seeds, one not on this list is hemp, and hemp's getting a lot of interest in the food industry as a potential new ingredient. All these ingredients have different pros and cons when you're looking at product development. So when we talk about different ingredients, we usually categorize them by the protein levels. And as you go down this list, you're increasing processing costs. So it's more expensive to make, but they're also higher value products. So it starts out with the lowest, whether it's meals or whole milled flour, ranging protein from 12 to 35%, or air classified protein concentrates, which are 50 to 65%, all the way up to isolates, which are greater than 80% protein. And then you can get some high value fractions such as bioactive peptides that could give some health effect and are quite pricey to make, but are quite lucrative at the other end. So we're going to talk about both dry and wet fractionation in this section. So why do we want to extract or fractionate? Well, it's pretty simple. We want to add value to the ingredient. So maybe we want to improve the nutrition and health components. Maybe we want to up the protein content in an isolate form, control amino acids. Maybe we want to remove undesirable flavor compounds to make it more consumer acceptable. We can also use it to fractionate to achieve different functionalities. We also want to enhance the utilization of co-products in different streams. But we want to really increase profits and market diversification. So when we talk about dry fractionation, it typically involves three techniques: milling, air classification, and screening. In the dry fractionation process, we can make flours, enriched flours, and protein concentrates. And these can then be used alone as ingredients or as a feedstock for the wet extraction process to try to up that protein content in that feedstock. to help with recovery, increased recovery of the protein in the wet extraction process. Dry fractionation is attractive because it has much lower costs than using wet processing, because we're not obviously using water or drying type approaches. So when we talk about milling, milling has a few different operations. Cleaning, where we're removing large impurities and screening them to separate them based on size, shape, and weight. It involves conditioning. So prior to milling, grain is brought up to a uniform moisture content, and that helps break open the outer layer of the bran, allowing for better milling and improved separation. And then milling, in which the main goal is to separate the bran from the germ and the endosperm, and then do size reduction to a uniform particle size of that endosperm. When we talk about air classification, basically this involves dispersing the flour in a flow of air, and particles start to separate based on size, shape, and density because of the upward push of the air and then downward drag of gravity. So this separates them into two fractions, a larger coarse fraction, which is dominated by starch, and a finer fraction, which is dominated by the protein. Now, each fraction is cross-contaminated with the other, so they're not pure, and we'll show some examples of this in the next slide. But there's a number of different air classifiers that exist based on gravitational or centrifugal separation. This is just some data from one of my master's students, Ashish Singhal, from the University of Saskatchewan. And what he was doing was looking at different faba bean varieties using the air classification scheme. A couple things I want to point out. So obviously the yield of the coarse fraction was 68%, and the fine fraction was 26%. So like most of the pulse industry, finding a home for that starch byproduct is really important to make it more economical. And there's a lot of work being done here at the University of Saskatchewan on that starch utilization side by Young Feng Ai. Next thing I wanted to point out was the faba bean flour had a protein content of 31, but when we did the fine fraction, we were able to get it up to 65.6% protein, whereas in the starch fraction, it still had 16% protein. And this is important because the protein in that starch fraction of the coarse fraction can have a big impact on their functionality as ingredients looking into product applications. The next stage is sieving or screening. This looks at controlling the size distribution of particles, which has a big impact on functionality. So size of these particles can impact whether it's the solubility or water or oil holding. We'll talk about functionality a little bit later in this talk. A number of things that can influence the sieving or screening process, such as the size of shape of particles relative to the mesh size of the screen, the amount of material on the surface of the screen, rate of movement of material on the sieve, so how fast it's vibrating, sieving time, the method of vibrational or tapping, and the material moisture. So all these can impact the particle size distribution that we get out the other end. Now, if we switch gears to wet fractionation basically involves extracting the protein from the raw material, let's just say a pulse, using a suitable solvent, which is in most cases an aqueous solvent. So the proteins go into solution, and the first thing that we do is we centrifuge out all the insoluble solids to get a supernate that's rich in protein. And then we can do, depending on the process, a number of techniques, whether it's adding dilute acid to precipitate the protein, using dialysis if it's a salt extraction, or filtration to obtain different protein profiles and fractions. So these can then be yielded into a wet protein concentrate or an isolate type product. This is just an example of alkaline extraction isoelectric precipitation process of a pulse protein isolate. So we use alkaline extraction to disperse the flour, maybe pH 9 to 10, allow it to stir in solution, then we centrifuge out all the insolubles. And in the supernate, this allows us to have be able to further fractionate that protein. So we can use ultrafiltration, different membranes. We can isolate the precipitate at different pHs to pull out different protein fractions that we may have interest in that could have unique functionality or nutritional properties. So we centrifuge these solids out, wash them, neutralize them, go through a pasteurization step, spray dry to yield your pulse protein isolate. The next wet fractionation is salt precipitation, and this is more done in the research or laboratory phase rather than in commercial production. In salt precipitation, basically people use ammonium sulfate, and at low levels it helps increase the solubility of proteins. It helps structure the hydration layer, but once it reaches a certain concentration, basically the salt water interactions are favored over protein water interactions, and what happens is that causes a disruption of the hydration layer as water molecules are pulled off the protein surface. That exposes hydrophobic groups, and then proteins aggregate by hydrophobicity. So depending on the concentration of sodium sulfate precipitation you use, you can pull out different fractions of proteins based on their hydrophobicity to create isolate type products. Another wet fraction technique is myocellulation. And here we basically dissolve a protein in a dilute salt solution, and we bring in the albumins and globulin proteins into solution. We clarify out all the insoluble matter, dilute with 4 volumes of cold water to help precipitate the protein, and the salt-soluble proteins stay in solution, form a milky white system. And then these protein myocells start settling out to the bottom, and then we can collect them. So basically the dilution encourages protein aggregation via hydrophobic interactions, which outcompetes any repulsive forces within the system. A good example of this is canola protein isolate that's being done on a commercial scale. When we talk about enhancing technologies, we're talking about how can we modify plant-based ingredients. So in this section, I'm going to really talk about proteins because they're their main value ingredient in a lot of these plant-based products. So the main goal of modifying these ingredients typically involves partially unraveling the tertiary or quaternary structures of the proteins, and basically we want to unbury some exposed reactive sites to change the surface properties of the protein, which then impacts its functionality. We may want to improve protein digestion or bioavailability of amino acids. We may want to reduce or eliminate anti-nutritional factors in the plant protein ingredients, alter functionality, alter flavor profiles, or potentially generate bioactive peptides in this process. Some enhancement technologies that people have used, and I'll give some research examples of these in a little bit. Infrared heating. So we have a company here in Saskatoon, Infrared Products Limited, which is really a global leader in infrared technology. And basically this radiation penetrates into the surface of the seed and causes water molecules to vibrate or rotate to generate heat. And that heat can then have an impact on both the starch gelatinization and the protein denaturization. Germination is another way that we can enhance technology. So here, grains or seeds are typically hydrated and then allowed to sprout under ambient conditions. This allows enzymes to start reacting within the seed, which then can impact proteins and starches and fats within the seed itself. Another enhancement technology is fermentation. We hear a lot about both solid state and submerged fermentation. But here we're incubating the protein ingredients, whether it's an isolate or a concentrate, with various microorganisms, whether it's Bacillus, Aspergillus, or lactic acid bacteria. And these organisms produce enzymes, metabolites, lower pHs, and this can have an impact on the functionality of the end ingredient. Enzymes is another enhancement technology in which they induce some partial denaturization of the proteins to expose these buried reactive sites. So it can change the surface properties and the functional properties. And the last enhancement technology I'm going to talk about is extrusion processing. Extrusion processing is a short time process in which basically the material is cooked in combination with temperature, moisture, mechanical shear, and pressure all in one unit and force out a dye. So we can pre-cook these flours or isolates or concentrates and then use them as is to make expanded products or mill them into pre-cooked flours as a pre-treatment and changing the functionality of these ingredients. So when we talk about crafting functionality, we're using processing as a means to alter the physicochemical properties, so the charge, hydrophobicity, the flexibility of ingredients. And then this can impact the functional properties, but also the protein quality. And when I talk about protein quality, I'm referring to the amino acid profile, the digestibility, and the protein digestibility corrected amino acid scores to define that protein quality. And then these can then impact product development at the other end in applications, which we'll talk about later in the talk. So if I give an example of some thermal treatments, the first one is infrared heating. And here, if you remember, basically infrared radiation penetrates the seed surface and causes water to vibrate to generate heat in the product. Typically, in the case of cereals or grains, we typically temper them to increase the moisture of the seed to increase that degree of vibrational energy generated. The results I'm going to talk about are published in Cereal Chem and Food Research International. So this is just an example of desi chickpea heated to 135 degrees Celsius with and without tempering the 20% moisture. It just shows the composition, and the protein and starch levels don't really change, but the gelatinization starch increases during that heating process. We also see a change in the surface charge of the protein, indicating that there's some change in the protein conformation to have exposed buried hydrophilic groups. Then when we look at the functionality, we see a decrease in the solubility from 69 to 43, which is the most amount with the tempering and the heat. We also see a rise in the water hydration capacity. So these highly charged reactive sites are being exposed to bind more water. And foaming properties and then foam capacity and stability both decreased. And that was due to probably reduced solubility of the protein being able to access that oil or the air-water interface. Interesting, the oil holding capacity and emulsion properties remained unchanged in this process. When we look at the protein quality, one thing that we noticed is that the in vitro protein digestibility increased slightly when we added the heat treatment, which makes sense because the proteins are opening up, they're starting to unravel. And more susceptible to digestive enzymes. And this resulted in an increase in the PD-Cas scores from 66 to 70%, so it improved the overall protein quality of the material. So if I give an example of a biological treatment, fermentation would be my first example. And here we're looking at two types of fermentation, solid state and submerged. So solid state, basically microbes are on water insoluble substrates with minimum water contact. And this is more conducive to fungal strains like Aspergillus niger or Aspergillus oryzae. Or submerged fermentation in which microbes, the substrate is submerged in water. This is more conducive to bacteria which like more water content in their growing conditions. Example of this could be Lactobacillus plantarum. So this picture on the right is just a picture of some pea protein, air classified pea protein in a solid state fermentation set. So it ferments as almost like a dough material. So this is some data, and this has been published in both Cereal Chem, 2 articles, in which we fermented air-classified pea protein enriched flour with Aspergillus oryzae for 6 hours. And what we saw is an increase in the degrees of hydrolysis during fermentation time. So the enzymes that are being produced are chopping up some of the proteins to partially unravel them to lead to this increased hydrolysis. We saw a slight rise in protein content as the bacteria grew and carbohydrates were used up from the bacteria. We also saw an increase in surface charge, which is an indication that the proteins are unraveling. And we saw a decrease in the surface hydrophobicity. And this was a different trend than we expected. We expected the hydrophobicity to increase. But in the solution assay, we hypothesized that as we increased the hydrophobicity of the protein, they re-aggregated to form larger aggregates, which then resulted in lower hydrophobicity values. The pH of the solution remained relatively constant until about 6 hours, until about 8 hours. Afterwards, it dropped abruptly to 4.3 from the 6.3. Looking at the water or the solid functionality, the water holding and oil holding both increased during this process. The solubility was found to decrease slightly with the fermentation time. And then emulsion activity and stability increase and decrease respectively with fermentation time. So we're seeing differences in the functionality as we process them to different extents in the fermentation process. The last one looks at protein quality. Here we see an increase in the in vitro protein digestibility similar to the infrared heating. However, we saw a decrease in the limiting amino acid score. So the bacteria were using up the methionine and cysteine first. And as a result, we didn't see an increase in that final PDCAS protein quality values that we're hoping for, despite that increase in digestibility. The last biological treatment I'm going to talk about is enzymatic modification. Here we're using the enzyme to preferentially cleave the conformation of the protein to cause it to partially unravel and expose hydrophobic and hydrophilic groups. It will also release peptides into solution. Now, different enzymes have different specificities. So the research that we wanted to look at was, again, using air-classified pea protein-enriched flour. How could different enzymes, if we cleave them to 2 or 10% degrees of hydrolysis, how would that preferential cleaving impact the functionality? So we chose trypsin, which preferentially cleaves at lysine and arginine, and pepsin, which preferentially cleaves aromatic or carboxyl amino acids. And this has been published in Serial Chem in 2 articles. So when we looked at the enzymatic modification process, we saw a slight increase in the protein content, and that was due to just how we treated the degrees of the enzyme treated samples. We saw a relatively increase in the surface charge, indicating that the proteins are unraveling. And we saw a big change or increase in the surface hydrophobicity as we increase the degrees of hydrolysis. And as you can see, trypsin and pepsin at the corresponding degrees of hydrolysis can have a big effect on the surface properties of the protein. When we look at the functionality, we see an increase in both the water and oil holding capacities as the proteins open up and combine more water and oil. And we saw variability in the solubility. So for the most part, solubility decreased. That was in part due to the higher hydrophobicity, except that the 10% degrees of hydrolysis pepsin didn't really change from the untreated sample. Here, the emulsion activity and stability was found to decrease in hydrolyzed sample relative to the untreated, and the foaming stability, capacity and stability decreased and increased respectively with the hydrolyzed samples. When we looked at the protein quality, again, we saw a slight increase in the in vitro protein digestibility, but depending on the limited amino acid score and peptides lost, we saw a decrease or increase in the overall PDCAS score. So it was dependent on the enzyme treatment that we used. So that ends my presentation. I'm going to stop sharing and pass it over to Mehmet for his presentation.
Thank you, Mike. So the next couple of slides, I would like to go through the formulated food systems, how we can use the plant-based proteins in direct expanded crisps and snacks, in bakery applications, in meat analogs, in flexitarian meat systems, in dairy-free applications, and also in the beverage systems. So overall, we'll go through a round of applications which are basically dominating the market at the moment, and these type of products are finding really ways in the food marketplace, and we are looking at a major growth in these type of products. So at the end of the session, please go through any questions, anything that we'll be glad to answer. So when we look at the direct expanded crisps, these are primarily, as Mike mentioned, it's basically produced based on the extrusion technology. So when we look at the direct expanded crisps, we have the possibility to use the plant proteins, the protein concentrates or the isolates. The overall, the factor how we can produce these products is really the texture, taste, and the sensory properties. Now, if you like to produce a product with much more crispiness, with more lightness, with more mouth melting properties, then we have to add more carbohydrates, more starch, so that we need to create more puffing and more expansion properties. And we have the possibility to add about 10, 15, up to 20% protein concentrates or isolates in these systems, and we can deliver the proteins accordingly where we like to deliver that type of protein at a lower protein level from 10 to 20% inclusion rate. Now, if you like to use the protein at the higher level, it's also possible to create these crisp type products, direct expanded crisps or extruded crisp type products. And we can use protein concentrates or isolates up to 80 to 90%. There's possibility to make any type of crisp products over 55, 60, up to 80, 90% protein. And we need about 10 to 15% some flours or starches to provide some of the overall assistance to the expansion process. But with these type of products, they'll be much smaller. They're going to be much more heavy in terms of bulk density, and they'll provide more crunchiness, more hardness, and more mouth melting and mouth drying impact, and there'll be much less crispy and the lightness. So overall, the plant proteins, they are like a really good fit for these applications. However, it's a matter of how we like to approach the overall product quality and what type of product we like to produce. So when we look at these crisps, they can be utilized in so many different applications. From Rice Krispies, we can produce low to mid-level protein levels in these Rice Krispies applications. Scotcheroos, different type of products. Again, we can deliver low to mid protein levels. And especially with these snack clusters, we can deliver high protein crisps in these formulations. And really the main factor driving the formulation and the product development systems in these formulas are the sensory properties, the taste, aroma, texture, and the protein content, the level of protein we like to deliver, and type of the texture, type of the taste, and the aroma in these type of systems. Moving forward in the extruded snacks, and extruded snacks has been really developed, especially in the plant-based protein industry, especially on the pulses with the pea snacks and mainly the green pea snacks. It's been established as a really reverse innovation from Asia. Asian countries, they developed most of these products in the late 80s, early 90s, and then through their innovations initially, these type of products developed into Asian markets, and now they are being widely accepted globally. And the main ingredients that we use here are the flours, the typical like a pea flour, yellow pea flour, green pea flour with 20-25% level. These ingredients are used with different starches or flours or wheat flour or different type of formulas. But now if you need to deliver the higher protein, it's also possible to add the high protein levels by using the proteins isolates or the concentrates, and then we can differentiate the products compared to the traditional puffs so that we can deliver the high protein levels in these extruded snack applications. And the main the differentiation here is the color, the taste, and the sensory attributes again, and the protein content. And there are several products in the marketplace, especially in Asian countries, but there are more and more examples coming to North America as well as in Europe and Middle East as well. And when we look at the direct expanded snacks with different type of products, if you look at the regular puffs, these are direct expanded puffs we can produce with single or the twin screw extrusion systems. In general, we use about 80 to 90% the flours, 10% protein and 5% fiber to create this type of puffy product, which we can deliver some protein. And as we add more protein, then the overall bulk density and the texture and the denseness of this product will change. They're going to have much higher bulk density. It'll be much firmer, and it's going to be much more crunchy compared to more like a fluffy type of texture. Again, with these type of products, we are looking at 80% flour, 10% protein, and 7 to 10% fiber. And with these type of puffs, they are a little bit more dense. We can push the level of the protein up to 15 to 20% protein level, with 70 to 80% flour, with 7 to 10% fiber. Now, when we look at the flours here, these are interchangeable. We can use pulse flours, we can use potato flours, we can use wheat flours. Any type of flour is possible as long as we have the starch presence, and that starch really is going to generate the texture and the expansion of these products. As we reduce the starch level in these products, then there will be less expansion and there will be more texture and more bulkiness in these products with the presence of the fibers and the proteins. That's why for the formulators, when we develop these type of products, it's really important to understand the micronutrients and look at the starch and the protein level, starch and carbohydrate balance, as well as the fiber balance. Moving into bakery. In the bakery applications, there are so many different unique properties that the plant-based proteins can be used. And again, the protein levels can be delivered with the flours, with proteins, protein concentrates, as well as with the protein isolates. And in these cases, the proteins, they are really used for dual purposes. We deliver the nutrition. So the number one factor to use these plant-based proteins are to deliver the protein quality. But also proteins, they also provide the techno-functional attributes, such as improving the moisture retention, improving the texture, the softness, the moistness of the product, elasticity, improved rheology. So plant proteins, whether it's a concentrate or isolate or with the help of some hydrocolloids or different type of oil systems, it's possible to come up with much more cleaner label formulation systems where we can remove some of the ingredients and make it more allergen-free, completely clean label. And that gives us the opportunity with the plant-based proteins in the bakery systems and the cracker systems and muffins, as well as more like saltine cracker formulations as well. Moving into texturized plant proteins, over the last 10 years, especially soy-free and the wheat-free market is really growing in this area, looking at texturized plant proteins, primarily from the peas or in the lentils and the fava beans. Again, in some cases, combining with the cereal systems and bringing wheat or the vital gluten again in these formulas. But when we look at the plant-based proteins for the meat alternative solutions, overall, we are looking at 80 to 90% protein. And it's a texturized protein, dry texturized protein with a meat-like bite with a fibrous appearance. And they can deliver the ground meat and the muscle meat alternative in any type of vegan formulation system. One of the benefits of these products, they have great water absorption, over 400% water absorption, and they are lighter in color and neutral in flavor. So the type of the protein we use, the type of the protein functionality we use, it is quite important for these applications. And the protein content for these texturized plant proteins can be between 50 to 80%. Fiber level can be variable between 5 to 15%. Saturated fat level is about 1% and no cholesterol. And in general, they're allergen-free and then clean label, especially when we talk about the pulse-based texturized plant proteins. So when we look at the texturized plant proteins, they can be texturized into different shapes, can be in chunks and slices, strips and granule forms, and then they can be formed into plant-based burgers, plant-based stir-fry applications, plant-based nuggets, as well as plant-based chili applications. The way that we add the water, the way we developed overall the texture of these proteins, the way we hydrate them, and the way that we form them, they are giving us the opportunity to create these type of different products, from burger to stir fry to nuggets to chili. and the level of the protein, the texturization property, the functionality of these texturized plant proteins, they are enabling us to use these products in several formulations. One example that we can use texturized proteins are the flexitarian burger systems. So on the left, you can see this is 100% beef burger. They are cooked more in a well-done form. This is the raw version, cooked version, and the cooked cross-section. And this is the raw cooked and the cooked cross-section. So the primary example that we like to feature here is the 100% beef and the texturized pea protein addition is basically, there's a major change between the cook yield of the product. So texturized plant-based proteins, they add about 10% more cook yield, and they add about 40 to 50% more technological yield compared to the per unit of meat. And in addition to that, when we look at the nutrition per 130 gram serving, by adding the texturized plant proteins, we can reduce the fat level from 26 gram down to 18 gram. We can reduce the saturated fat from 8 gram to 6 gram, and then we can deliver the protein level from cholesterol level from 115 milligram down to 80 milligram. And by doing this, we can keep the protein level the same, 22 grams. So it is very important to have this. And then by using the texturized plant proteins, we can reduce the overall the nutritional properties, and we give the consumers the opportunity to have a flexitarian system with much less meat. It's important to highlight that. Moving into some additional meat discussion, when we look at the meat industry is dealing with quite a bit of mechanically deboned meat in all over the world, in Asian countries, in Middle East, and other parts of the world. And when they produce these mechanical deboned meat products, there's quite a bit of this kind of low quality but edible meat tissues coming through the separation of the bone systems. And these products, they are utilized in different systems. We think that by utilizing these plant-based proteins in sausages and different type of hot dogs, or like a meat-based pastas, raviolis, or different type of formulas, the meat-based, combining with the plant proteins can really provide some sustainable, very innovative solutions in flexitarian applications as well. Moving into the dairy-free analogs, when we look at the dairy-free analogs, there are several different products, from cream cheeses to different yogurt systems to sauce systems and the custard applications. The deflavored proteins are really the key. I mean, the protein isolates or the concentrates, for these applications, they have to really taste good, and the sensory attributes have to be really acceptable, because we are competing with the dairy products, and dairy products, they have these unique tastes and the flavor. In order to mimic them, in order to give the same type of satisfaction to the consumers, we have to come up with the utmost quality in terms of sensory properties. So these products, they have to have that enhanced taste and the techno-functional properties such as emulsion and the solubility. And depending on the product application, from cheese or yogurt or from a sauce or any type of application, the inclusion rate can be from 3 to 30% inclusion rate with the right type of functionality. That's why it's important to use the right type of quality plant-based protein for these applications. Moving into beverages, again, very similar. In this marketplace, there are several companies, they are racing out, trying to replace the overall interest of the consumers to replace the milk products, traditional milk. And when we replace the traditional milk, the protein isolates or the deflavored proteins that we use, they need to have that enhanced taste and the techno-functional properties with the right dispersibility, with the right particle size, emulsion, solubility. And then these type of products can be utilized in formulations from 3 to 10% inclusion rate. And there's possibility to push them up to 15 to 20% with the right type of functionality. So again, it's a very active and a growing market. And with these type of beverages, the vegan beverages, the non-dairy beverages, the protein quality has to be at the utmost level for the consumer acceptance. With that, we'd like to thank you for your attention, and we really appreciate joining the webinar and look forward to your questions. Going back to Janita.
Yes, thank you very much, Dr. Nickerson and Dr. Tulbek, for a great presentation and detailing out how to craft the functionalities of these plant proteins to the product utilization. So there are questions in the question box. Probably we'll start with that first. One question is about isolates and concentrates. Is there a compositional threshold for each, typically the same across proteins extracted from various commodities? If I repeat the question again, with isolates and concentrates, are the compositional thresholds for each typically the same across proteins extracted from various commodities? Therefore, pulses versus canola and versus soy, like that. Can you comment on that?
Yeah. So typically, an isolate would have 90% or more protein. However, you find commercial pulse proteins termed isolates at 80% protein. So you do see variability in the market of the composition of these isolates in terms of the protein content. Same with the concentrates. So I've seen some companies report concentrates where they're around 50% flour, which is more of an enriched flour, whereas the concentrate should be up closer to 60%.
Yeah, a little bit. So that is on protein content, the composition threshold. That is how isolates and concentrates are separately identified based on protein content. And are there any other compositional differences between like pulses versus soy and pulses versus canola or soy versus canola? So a little bit more information I think will be helpful if you can comment on. Because concentrates comes with other material, because the protein is concentrated, and then depending on the plant source, either it is a pulse or a canola or a different plant species, the compositional differences are there when they make concentrates. Isolates are, we remove other components and get to the high purity of proteins. To my knowledge, it is depending on the starting material, there are differences. So in the industry, it is at this point, it is mainly based, the compositional threshold is based on the way it is processed. Is there any other comment you can bring it to this question that the member in the audience is asking?
I don't think I can add any more to that. I think obviously the way it's processed, it's going to have different levels of oil and fiber and starches. So I think, like you said, the starting material is going to have impacted. So all of those would have different compositional thresholds depending on what product you're working with.
Yeah, it's a matter of raw material and the process. I mean, that's basically the simple way.
Yeah, and the other thing, with pulses, one thing comes up is the oligosaccharide levels, because it is common for almost all legumes. How is soy versus pulses, the threshold levels for oligosaccharides?
I can comment on that. The soy, as a whole seed, the soy is almost double the level of oligosaccharides in terms of a whole soybean versus a whole pea, lentil, or fava bean. In general, the oligosaccharide, the raffinose, stachyose, verbascose levels, they're much higher in the soybeans. But as they are processed into a soy protein isolate or concentrate, they will have different levels. So the soy protein concentrates, they tend to have much higher levels because it's only the oil is separated through crushing, and it's a combination of the protein and the carbohydrates, and there's a considerable amount of oligosaccharides there. But as you move forward in the isolates, those carbohydrates, the overall oligosaccharides, they are separated, and they are basically in the industry, they produce the soy isolate at 80, 85, 90%. Same for the pulses in general. The dry fractionated proteins, the protein concentrates tend to have some oligosaccharides. As we move into more isolate type products, they are basically zero. So all of them, they are separated through the wet milling and the wet separation technologies.
Yeah.
Good. Another question on macro trends. How are conversations regarding processed, unprocessed, etc., affecting the value-added ingredient sector?
Well, I think obviously the level of processing in the clean label process, I think it's not viewed poorly by the consumer or the industry. I think processing is really important to get these protein isolates or ingredients that can offer enhanced nutritional properties and functionality of your products to make these plant-based products. But using clean label approaches, whether it's enzymes or not using chemicals, is really important from the clean label perspective for those ingredients.
And just to add to Mike, it's a matter of cost as well, Janita. I mean, as we apply more process on these raw materials, as we add one more step, another step, then the level of cost and the process will go up too. And then that's going to reflect to the raw material, the product cost, which will reflect onto the consumer. So in general, the less the process applied into raw material, of course, it's going to have much more native or more natural type of appeal in these products as we go further down the process. Again, they can be more clean label, but the level of process will definitely increase the cost too. So that's going to be another factor.
Yeah, then again, your examples show very well. The minimally processed ingredient is the flour from pulses. When they go for direct expansion products like snacks, what are the taste or the texture qualities they can bring? It's more towards fluffy. Then you add more processed protein into that product, which is a processed ingredient beyond flour, just milling, and the texture can be changed to more hard and firmer product. So at the same time, then added cost, and it compromises the less processing, sometimes compromises the outcome of the ingredient in the product application. That is what I believe, that is what I see you showed. And at the same time, as Michael said, there are other options. So processing with less chemicals, less less alterations, but still to achieve a certain degree of change through natural processes like fermentation using microbials and enzymes, those kind of ways. Yeah. There's a question about blending of plant proteins. Blending of plant protein is used to increase the protein quality. How does blending various ingredients and protein affect functionality in food applications? I believe the question is various ingredients means still it is it could be from different protein ingredients, or it could be from like salt, sugar, oil, this. And so it is little two ways I think we can discuss this, answer this question.
Yeah, we've done a lot of work on blending cereals and pulses together, particularly chickpea, and we looked at sorghum, maize, and and barley. So we do see differences. So we blended them based on their protein quality to try to match up their amino acids profiles, but they did have a big effect on functionality as well, especially whichever one is a dominant protein source. It tends to behave more like that. So it's not a straight trend when we talk about functionality when you go from a ratio of cereals to pulses. But it's typically whatever's the more dominating protein in terms of quantity. The functionality sort of behaves closer to that as the raw material.
Just one thing to add to Mike, in addition to the protein quality in those systems, you should think about the other macronutrients in that system, like the chickpea starch versus sorghum starch versus barley. Barley starch, and barley has beta glucan and other type of ingredients, so the level, and it's going to have more mucilage and more stickiness. So the type of ingredients you use in a formulation, it's going to change the entire functionality of that system. How you extrude it, how you process it, how you bake it, how you mix it. So it's not only sometimes in these formulated systems, it's not only a protein question, but it's more like a complete delivery system question. By doing this right protein, well, we may affect other things in the formula. So it has to be really thought thoroughly.
Yes, micronutrient delivery is a consideration always. Exactly. At the same time, some of the examples that Mehmet showed, blending with meat, the plant protein ingredients, blending with meat ingredients. So meat is mostly protein and water, and sometimes fat comes with that. So then protein quality is one thing, and at the same time, the functionality enhancement or optimizing functionality the blend can bring with keeping the improved protein quality is a challenge too, but it can be done.
Yes.
Yeah. Okay, there is a good question on flavor. What about earthy flavor, beanie, cardboard flavors provided by plant proteins? How we can overcome this challenge?
Mike, you want to take it
first? Yeah, there's a couple of different strategies. There's the breeding strategy, where in some cases they're trying to lower levels of lipoxygenase enzyme to reduce the flavor compounds. But in terms of processing, there's various things in terms of thermal treatment. So infrared heating, steam injection in your wet extraction process. Some pasteurization blows off volatile compounds. We've done some work on absorbent resins and alcohol washing. Now those both affect the functionality of your protein at the other end. So usually when you start modifying the flavors, you also have to look at the protein quality and functional properties and what's the consequence of those flavor reduction strategies.
Yeah, just to add on, Mike, in general, these flavors, they're quite a bit of heavy in terms of aldehydes. And these aldehydes, they really create quite a bit of flavor in these proteins, especially when they are in native form. And all the technologies Mike stated, from solvent extraction, alcohol use, water alcohol blends, or thermal treatments, hydrothermal treatments, everything, they apply a certain level of removal of this off flavor and the flavor and taste, but there's also an exchange of what do we lose. As you apply more thermal treatment and all these processes, you may lose functionality, you may lose other things. So there has to be a balance with the process versus the taste and the sensory properties. So that has to be really balanced in there.
Okay. There is a question about expanded snacks and other applications. How the cost of these ingredients compare to traditional ingredients in these applications? Is this a barrier to use at the present time? Are there any challenges with flavoring?
If this question came to me a couple of years ago, I would be a little bit concerned. But now with the rising commodity prices, what we are seeing this year and overall the next couple of years with the COVID effect, we may be quite competitive with these plant-based proteins, flours, different ingredients, and with the interest of the consumers. These products, they may really fit well in the formulation systems, can be slightly higher than corn, wheat, this typical cereals. But again, when you look at the level of protein delivery, the level of the impact of these ingredients in the nutritional level in terms of like the consumer impact. So I believe it is out there, and now with the rising commodity prices, will be more competitive in these markets and snack, bakery, and other applications as well.
So are there any challenges with the flavoring of these products? Like I know cheesy flavors, so they are more retain more? Or?
Yeah. No, not really, Janita. In terms of the flavoring, again, you know, it's a much deeper question for the flavor houses, but based on our experiences in general, they tend to work very well compared to the other cereal products. Even with basic flavors or different type of flavor systems, we can use them in a very similar way compared to cereal-based snacks or wheat-based, corn-based snacks or different blends. So we don't see a major difference, any hurdle in the flavoring issues with these ingredients.
Then goes a question on textured meat applications. Do serving sizes typically lead to source of protein claims, or is blending with other plant protein or animal protein usually required?
It depends. It depends on where you are, your geography. In North America, it may be. In European Union, in general, the overall the protein claim can be basically can be reached by the level of the protein per serving size. So in these cases, it may be easier because they don't use PDCAS or any type of protein rating system in EU regulatory agencies in EU countries. But when we look at North America, we have to follow PDCAS, PER, different scores, and we need to look at the exact PDCAS level. And if the PDCAS level is not high enough, then we need to bring maybe additional proteins, look at the PDCAS, calculate based on the serving size. So it will depend on the formulation. It may or it may not. It's a specific question that we need to look at it based on that particular formulation.
There's a question about how important is to defat pulses in order to produce protein isolates and concentrates.
Mike, you want to take that?
Yeah, obviously the presence of lipid can do two things. One, it limits you have reduced protein extraction efficiency because it promotes protein lipid interactions, but higher levels of lipid in the powder at the end product can also impact functionality but shelf life of your ingredients. So at the same time as if you remove the lipid with hexane or something, it's not really a clean label approach to doing so. So there's a trade-off of removing the lipid versus doing it or keeping it. For pulses and peas, they typically leave it as is, but in chickpeas, they would have to deflavor it just because of the higher amount of lipid present.
Yeah.
Yes. Again, it comes to the level of lipids of the starting material too. Like chickpea and lupine, they tend to be high in oil content. So it is good to consider a removal at the upfront. This question is particularly to Michael. How you measure surface charge and surface hydrophobicity?
Yeah, surface charge is measured using a machine called a zetasizer. So it's made from Malvern Instruments, and basically it measures the electrophoretic mobility, so how fast the movement of a protein goes between two electrodes. So from that speed, it can calculate the charge of that protein, about how fast it moves within that between two electrodes. So that's surface charge. For hydrophobicity, we use, there's a couple different approaches you can use. In our lab, we use two intrinsic fluorescence, which looks at the intensity of the fluorescence of aromatic amino acids. But we also use what's called an ANS probe method. So it's a fluorescent probe method, which binds to the aromatic groups. So if you have a protein that's more denatured and has more exposed hydrophobic groups, there'll be more fluorescence generated through that process. So that's how we measure both of those in our lab. There are other methods, but that's what we use.
This question is there a type of plant protein isolate that is good for emulsion stability, particularly for high internal phase oil-water emulsions for fat mimetics?
That's kind of a hard question to answer. See, I'll give an example. Processing has a huge impact on the end functionality. So if you have a pea protein isolate made from 10 different companies, they're all going to have different functionalities for that product. Now, in the lab where we have greater control over it, we've looked at the emulsion stability of peas, lentils, chickpeas, and faba bean. And what we found was lentils had superior emulsion properties compared to pea, but chickpea and faba bean were also quite high as well, a little bit better than pea. But to your question, it really depends on how that protein ingredient was processed, of how the functionality is going to be, and it really is different for each company that produces it.
Right, that's true too. If you take soy protein industry, and if you take one company, company A, it produces several types of protein isolates. And then if you go to technical descriptions of each product, it says good for emulsion stability. And the second product will be good for solubility based applications, so like that. So it is at this point, I think we can manipulate the protein to be a better emulsion stabilizer rather than going from its botanical origin. I think that's those are the questions that audience has brought. I have a question. Have you tried, because Michael's presentation showed we can alter functionalities and also including flavor going through fermentation. So fermentation we can consider as a clean label process. And then Mehmet's presentation showed extruded products. If we use flour versus the protein product, the different of textures and texture profiles we can get. What is your experience with using fermented protein material or flour material in extruded products?
We haven't done any work in using that. We've just started working in our lab using the solid state and submerged fermentation to modify protein functionality, but we haven't to a point use it fermented stuff in extrusion products.
Well, what I can say, Janita, to me, we don't have that much experience. These are some new products that's we are been working on, but the level of fermentation and the impact on the starch is the key for these products, because if there is any degradation in the starch, then that's going to reflect, especially if it's a flour or a concentrate, that's going to reflect in the final application, that we are going to see much less expansion or different things. In terms of a protein functionality, compared to regular versus fermented protein, I don't expect a major change in the extrusion systems and snack systems, especially about the overall degree of fermentation in especially carbohydrates in starch can make a major impact. So there will be more work needs to be done in this field, and I will look at more applications in the future.
Yeah, definitely. I believe this is a growing area. So whatever advantages or a bonus that gets from processes like fermentation, whether it is stable or the improvement is retained in product applications. So that is an area that both industry and academic researchers has to explore.
Looking at, yeah.
Okay, good. Looks like we don't have any other questions. Any other comments you would like to make, Mehmet?
Thank you.
Oh?
Thank you. Thank you. Thank you.
Okay.
Thank you very much.
Yeah, and on behalf of AOCS, I thank you very much for great presentations and great discussion. So that will conclude our presentation, conclude our webinar. And thank you very much for joining us.